In this chapter, we will understand the definition of raster deliverables. We'll comprehend the difference between the DSM and the DTM. And we'll want you to become familiar with the orthomosaics editing techniques and familiar with the various raster visualization options. And also, I want you to learn how to locate the deliverables. Now, in the previous chapter, we explored the dense point cloud, and we understand that DPC is not just a standalone deliverable. It is considered a building block from which numerous other deliverables are built upon. In addition to the 3D textured mesh, the raster deliverables are derivatives of the DPC. Unlike triangulated network that the 3D textured mesh is built upon, rasters are interpolated images that contains rows and columns of pixels. Now, each pixel will have a digital number or DN value associated with it. The DN will commonly represent either a color value for a photo or an elevation value for a topography. In the geospatial lexicon, rasters are in reference to a photo, are known as orthophotos, orthomosaics, or simply orthos. There are three components that make up an ortho. Photos are rectified, meaning distortion is corrected in order to provide a geometrically accurate representation. Multiple photos are mosaic, meaning the rectified photos are glued together to form one large photo representation. A uniform GSD is applied to the pixels of the orthomosaics. Furthermore, rasters that are in reference to topography are known as digital elevation models, or DEMs. Interpolation of elevation occurs to a pixel when a direct elevation coordinate from a DPC is unavailable. DEMs are commonly used for two purposes: when the elevation of the ground as well as all of the above ground features need to be represented. This is known as a digital surface model, or a DSM. When only the ground or bare earth needs to be represented, this is known as a digital terrain model, DTM. Now, during step 3 processing, the orthos, DSM, and the DTMs are deliverables, which the user can generate. Now, these deliverables are commonly used in GIS software. So in this chapter, we'll explore tools that edit and manipulate the rasters. As with our previous chapters, we'll be working with pre-processed projects. The project data and the images are located in the L8 data zip file, and you'll have that either by the professor giving it to you or it can be downloaded. We'll open that file up, and we will extract that and then move the L8 data file over to your last name Pix4D file, as we've done in the past. And once that gets copied over, we will take a look at the contents. In doing so, we'll open up the Pix4D file, and we'll go to the L8 data file. And if you notice, it's 01 and 02 again. Images are in 01, project is in, and of course we can verify that. And then when we go to the project, what we want to do is we're going to double click on the Pix4D file, which is a rasters Pix4D file. And when that comes up, it may want you to redirect the location of where the images are, like this. And we will do so by going over to the image file for the L8 data. And when it loads up, it will load to the raster file. This particular project was flown in Richmond, California. And it's actually the same project we did in, I think, the earlier chapters, or the first chapter. So for this one, we're going to click on the Mosaic Editor. And after loading, the ortho will be displayed in the data view, as you can see here. Now let's zoom in with our mouse, and we'll just kind of click and pan around the area So use the tools that you have learned in the past, and let's take a look at and get familiar with the area. Being that the ortho is an image, there are inherently places within it that contains artifacts, and we'll use the regions tool to edit these artifacts. So if we zoom our mouse into the south central portion of the ortho, of which you see in my video here, you focus your eyes on the driveway that goes into the parking lot, and we'll notice that there is actually an artifact right there. Notice that this is a white car that is driving into a parking lot. It appears as though there are two cars, but if we really look closely, you can see in reality that this is really the same car. Also, the cars appear to have an odd transparency to them. This artifact is known as ghosting. When an object moves in reality, it becomes located in two or more positions in the image set. In other words, it's located in one position in one image, in another position in another image. The dynamic nature of a car in a parking lot makes them commonly susceptible to ghosting. And as you move in a little bit closer, it becomes really apparent where the ghosting is. If you look at the right side under the mosaic editing, under regions, you'll see a button that says draw. So you want to click on that. And then notice that when you move your mouse over the ghosted car, the cursor changed from an arrow to a crosshair. So I want you to do is position your crosshair on the asphalt near the cars. And use the left click of your mouse and begin to digitize vertices around both cars. And when you're done, just right-click your mouse to close the polygon. And when you complete your region, the ghosted cars look actually much better. What happens here is that the software creates a patch. What happens here is that the software creates a patch of image content from one of the original images before rectification within the region. Notice that the image window on the right of the screen that you see down here, and select the image that basically says 0007. The patch within your region, if we select that, it will change the content. So if you notice that it's changed from the original content to the content that was in 0007. So basically are swapping an area. Regions are an excellent tool to remove and edit unwanted artifacts from the ortho. Now create a number of additional regions or artifacts that you found. To do this, click the draw button once more and follow the same procedures. To return to a specific region and edit it after a number of other regions have been established, select the drop down from the near the draw button, and notice as you choose different regions, they become selected in the data view. It's possible to add and edit as many regions as one desires. For an example, we see the car just above it, and we can go over here and draw that one. And we'll go around this one as well. And then we've noticed that on, say, 009 is the car is not there, so we can select that region. And bingo, it disappears. So at this point in time, let's click the Save button. Now, if you do get some errors, that's it cannot find files or and this sort, you want to stop and then go to the processing and select all three steps, and then start the processing and let it continue till it's done, and then go back and then do this process over again, because some of the files may not have been transferred over appropriately within this chapter. But after you, if it does save successfully, then you export it, of course. And like I've mentioned, the TIFF can be then found in the 3 DSM Ortho folder located in the parent project folder. Now, if you exit the software and fail to save the ortho, the regions will be lost altogether. So if you fail to export the ortho, the regions will be lost, and you'll just have to do it again. In addition to the orthomosaic, step 3 generates DSM and DTM as raster formats. Now we'll review different ways to visualize the DSM next. Now locate the mosaic editor on the top tab up there and bring that down, and then see where it says view. Click on that, or actually just highlight that. And a number of features are available that you can turn on and off. And by clicking them. In our example, let's just click show regions, and we'll also click show edited mosaics, okay, and check them. And then while in the view, we're going to then click on show DSM. And the DSM, as you can see, has been visualized instead of the orthomosaics. Now move the mouse over and click visualization. And if you noticed that on the far right, this will brings up the visualization window. And notice that the histogram under the band information and since the pixels in the DEM rasters represents elevation values, the image is a single band. The min-max values are the lowest and highest point on the DSM respectively. And the graph shows a full spectrum of pixels that make up the DSM raster and plots the frequency of elevation values. The spike of pixels from 11 to 25 means that most of the areas has an elevation somewhere within that range. And in reality, it's a pretty flat public parking place. Now, let's locate the data band range value, which is under color mapping. You'll see single band, and under it says data band. And what I want you to do is the first one is the minimum value. Let's set that for 11. And then we're going to set the maximum value to say 25. And then we're going to click the update button, and it will update. And notice the DSM color changes. We have isolated the park to pop by constraining the elevation values that are appropriate to it. The large hill to the east of the park is much higher elevation, and then the values are displayed as a maximum, which is in the red. Furthermore, the palette may be adjusted to colorize the elevation values to a different preference. When enabled, the shadowing option enables the hillside effect to the DEM. And lastly, the ordering may be switched to display the elevation values to min or max. Each time a color mapping option is changed, the update button must be clicked for the changes to take effect. Adjust the palette and select the option. And select the option. Let's see, under palette, let's select the option to be spectral. And then we select the option to min max, which it is, and then we click the update. And as soon as it updates, we notice that the changes of color to the DSM. Confirm your DSM looks like the following, and choose your own setting. And notice that when I change the ordering from min to max to min, this actually gives us the lower end as in red and the higher portions in a more of a darker spectral color. Now, as mentioned, the DSM represents the elevation of the ground as well as all above the ground. To remove the above ground features from the model, the processing option called Raster DTM must be checked before running the process for step 3. In this data set, the DPM has already been processed and ready to be visualized. As you notice, I've changed a few things around in my spectral band just to get a different color. So I want you to experiment with that a little bit, and then we're going to come back and actually going to click the tab again. And actually we can do this by the center tab up here and just look at and we can just kind of go back from DTMs, DSMs, and the mosaics as well. This visualizations can really assist you into continually to adjust it, and by looking at the trying to eliminate the removal of the ground features is typically an automated process. But it would be appropriate to perform quality checks of the software performance of this task. And this is the easiest way to do this, is to locate a known feature on the map by toggling back and forth. And then once identified in the ortho, you can toggle the view to DTM to see if the elevation is flat where the feature exists. And that's why when you're up here into the center, you can just easily toggle them back and forth to make sure that the feature has been removed if possible. Now, if you click the variety, I want you to experiment with the mosaics and the DTMs, and then go back, and if something is not flat, adjust it, and to see if in fact that you can get it to where you want. Now, what you want to make sure of is that you have you're able to correctly remove the above ground features. For an example, let's take about the shed. See if you can't correctly remove it, including the vegetation. Now, the vegetation is dense, is a little problematic. It is known because the vegetation is a distinct yellow color, and it will probably show higher elevation than the ground. Since the DTM is a direct derivative of the DPC, it's important to revisit the DPC and manually classify the vegetation to a proper group. To review how to classify DPCs manually, refer to a previous chapter of a technique that we've used in the past. Now, after you do that, all of the rasters will need, of course, to be regenerated and reprocessed in step 3. So now let's look at locating the deliverables. Deliverables are meant to be delivered and open to third-party software. From here, further analysis or processing may be conducted. It's important to understand where the deliverable files are written so that they can be accessed. Now, as long as the user chooses to do so, deliverables are written as a specific digital file. Files are written during the process of a step. For an example, a TIFF file that represents the orthomosaics will be written during the process of step 3. A series of different file formats are available to be written for the DPC during the process of step 2. Now, locate the open results folder. So if we go up on top, you can see the open results, and we click on that, and the window Explorer, as you see, opens. And the folder path will be directed to the project folder, which it is, and the files are labeled according to the steps which have been processed. The naming convention is always the same. The _initial contains files that the software relies on to align and orient the photos and the ATPs. Also contains the quality report. While the folder is necessary for Pix4D Mapper to work, there is no deliverables of significance located in that file. The next one that contains the DPC and the 3D textured mesh deliverables. The next file, the DSM Ortho, contains all of the rasters deliverable discussed in this chapter. So if we open that file, and next open the one DSM file, notice all the files here. Copy and paste the files to another directory on your computer. It's important to copy all the files and keep them together. So if you want to, you can open a GIS software like ArtMap and load the TIFF files of your DSM. You now have a functional GIS layer that may be analyzed. So the purpose of this chapter was work with raster deliverables. The orthomosaics can be edited by using the regions tool set. The DSM and DTM can be visualized in a number of unique ways. Step 3 generates and writes the files for most of the deliverables that can be derived by Pix4D. So now once you go up and click the, let's get out of this one and go up and click the projects and say save as, say project as, and ensure you're in the O2 directory, which you are. And then give it your last name, underscore, and then say L8, and then click the save button, L8, save button, and we'll let it save. And then then you want to navigate to the O2 project folder for L8, select both, zip it just like before, and then give the zip file to your professor. And that completes the chapter, the last chapter.